Our next speaker is Predrag Gruevski. I only have one note for you that was provided by Tertz, which was to ask, I don't think this is me asking, you should ask Predrag about the time he went to watch a giant rocket explode. That does sound like fun. Predrag is going to talk to us about what it'll take to eradicate unintended breakage from Rust, and let's give him a hand.
Thank you. It's a pleasure to be here. Like Adam said, my name is Predrag Gruevski. You might be familiar with some of my work on cargo SemVer checks and the trustful query engine that powers it. And right about now, you might be thinking, I didn't mention being on any Rust project teams, so what am I doing in this room? The answer to that question is that my work necessarily touches the work of many other teams. Definitely Lang, Cargo, rustdoc, many others. And so as a result, I end up finding all sorts of interesting things in the Rust language, some of them intended and some of them less so. Like, for example, when adding an import can cause a major breaking change. That I don't think was ever explicitly designed into the language on purpose, but it is the reality of Rust as we have it today. I also write explainer blog posts because I need to deeply understand various features of Rust, like how does trait sealing work? Trait sealing is not a language concept, but it is a reality that many crate maintainers use. And so cargo SemVer checks has to support it correctly, or else it will just produce categorically incorrect results. It doesn't matter that this is not a language level concept. It is a concept that cargo SemVer checks needs to know about. So I'm here essentially as a consumer of the output of many teams, and also as an interface toward many of the maintainers in our community. Because when they run into issues, oftentimes I'm very curious to learn more, and therefore I have a very wide purview of what is going on in the Rust ecosystem, and I'm hoping to distill some of that in this talk. So the purpose here is to give you some intuition of what Rust looks like from my point of view, both toward the maintainers, the consumers of Rust, and also how the output of various teams in the Rust project looks to me. And with that, let's get started. I'll start off with a hot take. Unintended breakage is bad. It is a lose-lose proposition all around. Maintainers are in the frustrating position of having never made a concrete decision to break something to be responsible for the fallout. They have to triage the GitHub issues that get raised, they have to remediate the breakage, and oftentimes they leave their users stranded. Users also have a bad time. They never signed up for that breakage. They just ran cargo update and now their project doesn't build. That sucks. And this also sucks for every one of us as a Rust community, because it teaches us to not trust our tools. Cargo update is not fearless today. And that's unfortunate, because it means that we don't update our dependencies as often as we could. And so we don't benefit from the bug fixes, the hard-won performance gains, the security patches that get shipped, and so on. So we're all living every day with worse software. So unintended breakage is bad. Let's assume that we've decided to make it a goal of the Rust project long-term to eradicate unintended breakage entirely. What would that look like? That is the point of this talk. So the framing is very simple. Alice is one of our users. She runs cargo update. Her code stops working. This might sound like a hypothetical case. It is very, very much not. A cargo SemVer check study run across the top 1,000 most popular crates in the crate ecosystem in 2023 revealed that we ship, on average, about 1 to 2 SemVer breaking releases every week. More than 1 in 6 of those top 1,000 crates has shipped accidental breakage at least once. So this is a very real thing that happens even to the most expert maintainers. So this is the reality of Rust today. We might not like it, but those are the statistics. And more importantly, this is a study from 2023. This number is definitely an undercount, because cargo SemVer checks has more than 4 times as many lints today. So if we redid this study, we expect that number to go up, not down. Some assumptions and some ground rules for this talk. The first and most important one is we're not solving a security problem here. So everyone has the best of intentions. There's no malice. People are not breaking stuff on purpose just to be annoying about it. We're also not going to assign blame to anyone. We're going to categorically reject the concept of human error. So it is a bad system when it lets well-intentioned users down, But just because a system is bad, it doesn't mean that we're going to throw the designer of that system under the bus either. Every one of us here is doing our best, and we're all trying to improve how things work. And that starts by pointing out where systems could be better. So we're going to take the mindset of, here are the places where things need to be better, and let's figure out how to get there. We're not going to assign blame to anyone. And a bit of a meta point, we're going to say no shutdowns. So let's all adopt the mindset of, it could work if, not this will never work because. This is a very important and very personal rule to me, because when I was starting cargo SemVer checks, I was repeatedly told it will never work. I was told, we've tried this 3 or 4 times in the Rust ecosystem, and the project failed every single time. So here's a laundry list of features why this will never, ever work. So it's just not even worth trying. Like, let's just save you the time and tell you not to bother. And yet, here I am, and here cargo SemVer checks is more than 3 years later. It's used by a vast fraction of the Crates.io ecosystem. So I think the news of its demise was a little bit overstated and premature. All right, so Alice has run cargo update and her code has stopped working. What this means is that some other maintainer, Bob, has released a new version, and something happened with that new version that when it got picked up by cargo update, the project broke. Okay, so let's play Sherlock Holmes a little bit and try to put on our detective hats and figure out what happened and how. There are a few different options. The obvious one is that upstream broke SemVer, right? So there is a major change that got shipped in a version release that was not major. Cargo update picked it up, and now the project just doesn't build anymore. Cargo check just fails with some compiler error. The natural question here is, why did cargo SemVer checks not stop this, right? We would have expected that the maintainer ran cargo SemVer checks, and then they decided to move forward. And in order to understand this, I want to tell you a little bit about how cargo SemVer checks works. The idea here is that if we're going to release version 1.1, we want to compare the API against version 1.0. And if there are any breaking changes between those two versions, we want to flag them and say, hey, this version might not be right. 1.1 might not be the right version number. You might need 2.0. The way this works under the hood is that we will build the rustdoc JSON for the proposed version 1.1, and also for the already published version 1.0, and then we will compare them. So we will look for breaking changes between the two rustdoc JSON files. Just to give you a little bit of intuition about where time is spent, about 90 to 95% of the runtime is in actually building the rustdoc JSON files for us to inspect. And then less than 10% of the wall clock runtime is actually inspecting the rustdoc JSON files and looking for breakage. All right. To give you a bit of a sense of what these checks look like, here are some very real lints. So let's say a public function used to exist at some publicly importable path, and it no longer exists at that path. So that is clearly breaking because you can't import that function and use it anymore. Another example is a public function takes a different number of arguments than it used to before, so this is also clearly broken because any of the calls that supply the previous number of arguments will just not work anymore. We have about 140 other lints in addition to these, and the number of lints is growing exponentially. And when I say exponentially, I'm not exaggerating. It is quite literally exponential. It is doubling every year. So this is not a trend that will slow down anytime soon. And in fact, we're currently ahead of the curve for this year because we have hundreds of lints left to go. So broadly speaking, if there is a rule and we don't implement it yet, then try again tomorrow. The news might be different. So why didn't cargo SemVer checks catch our example of breakage? Well, there are two options, 80-20. Option number one is we haven't implemented the rule because we don't know what the rule actually is. Like, when is the thing that happened breaking? And option two, we do know the rule, but we don't have the necessary data. Rustdoc JSON or some other component just does not ship us sufficient information for us to have detected that breakage. We're going to dig into both of these one at a time. And there's actually a secret third option. Shh, don't tell anyone. The rule involves types. There's type-related breakage. This is not something we're going to catch today, and it's one of the surprising things about cargo SemVer checks. There's a good reason why we don't already have it implemented, but we are actively working on it. So if that's something you're interested about, please ask me later, and I'm happy to talk about it. It's not a main part of this talk, though, so I'm going to just set it aside for now. So let's just dive right in. Option number one, we don't know what the SemVer rule is. In order to figure out what is the SemVer rule, we need to essentially rules lawyer a little bit and figure out what exactly might be broken, and how could we possibly convince a user that the thing that we claim is broken is actually broken, right? So in an ideal world, we would have a concrete Rust program that we could show the user and say, this used to work, and this doesn't work anymore, right? And so this is a breaking change within the spirit of RFC 1105, the API evolution, and other normative documents in the Rust ecosystem. The difficulty here is that Rust is a big language. There's a lot of things to think about. There's a lot of features, and there's a lot of interactions between those features. And so this is much, much easier said than done. In practice, this is actually the hardest part of writing cargo SemVer lints, just figuring out what the lint should be, what should we catch. And there are 4 themes that I want you to look at as I show you a couple of examples of this in practice. One is that we need to do a lot of research. The rules are not written down. It's not like we have an exhaustive list and we just need to check a bunch of boxes. We need to figure out what those rules are. In order to figure them out, we need to do a whole bunch of experimentation. And in order to make sure that we get the right rule, we need to handle all of the inherent complexity in the Rust language. All of those interfeature interactions need to be thought about, experimented with, and researched. And then finally, there's a lot of risk, because if we get this wrong, then bugs happen, both false positives and false negatives, and those are both bad, and we'd like to avoid them. So we really want to be right, and that requires that we be very, very thorough in this step. That's why this takes so long. So here's an example. I was recently looking at the target feature attribute. If you're not familiar with it, it just allows Rust functions to say, the following features must be present on the hardware where this function is running. And there are several different ways to use it. The details are not super important, but I'm happy to tell you more about it later if you're curious. And this is just me beginning to look into this feature and writing up essentially a lint report. These are the following things that we need to catch. These are the SemVer hazards and proof, how we would convince a user that something is a hazard, and so on and so on. So this issue is the product of many, many hours of my work. As you can see, there's experimentation right there. There's a playground link. I wrote a piece of code, and then I had to go check it in the playground to see if a thing that I suspected might be breaking was breaking or not. What I'm also not showing you is the many conversations that I had with people in this room to help me understand this feature, which obviously, is never written down in the GitHub issue, but I'm deeply grateful to everyone that helped me. This is the rest of the issue, by the way, because obviously it doesn't fit on one screen, even on this big one, even on this one big screen. And there are a couple of interesting things you might notice. One is that as I was thinking about SemVer hazards, which are necessarily some sort of inconsistency between different package versions, it turns out that you can write an inconsistency within the same version. And if you can trigger inconsistency in the same version, we call that Lang unsoundness. We ended up, the Rust compiler ended up accepting a program that it should not have, a program that is self-inconsistent, that specifies different things in 2 different places. So this research was already useful. We haven't implemented any SemVer lints, but something good came out of this. Thankfully, this inconsistency is not something that's likely to come up terribly often, so we should be able to close that hole without making too much of a fuss about it. But it's still nice that we managed to find a gap and address it before it bit anyone. And the other thing you're going to notice is that after many hours spent on this, the issue ends with a list of open questions. And this is because I'm not an expert in this feature. Like, I spent many hours learning about this, but I'm still a noob. I've never used this feature myself in any of my crates, so this is just my best understanding of how things work. And that understanding is necessarily incomplete because I'm not the expert on this. And then after I wrote this issue, a handful of helpful folks jumped in and offered some suggestions, helped me close some of those open questions. And then there was more work and more discussion, and some more work and some more discussion, and some more work and some more discussion. And at this point, 0 lines of code or lints have made it into cargo SemVer. This is what I mean when I say the hardest part of writing new lints in cargo SemVer is figuring out what are the lints to write in cargo SemVer. That's why this is hard. When this process goes wrong, we get issues. Here is a false positive where cargo SemVer was incorrectly detecting that a trait was sealed. Now, trait sealing is a topic that is complicated enough that I would need a separate 1-hour slot to walk you through it. So, of course, please ask me about it in the Q&A if you're curious. But in this case, we were categorically getting the wrong answer. We shipped an update to our trait sealing analysis, and it was just wrong. Within a month, 3 different projects chimed in and said, hey, you broke us. And it was wrong in a tiny little edge case. The fix was 1 line of code. We had more than 2,000 lines worth of test cases that were written prior to this, and none of those test cases managed to find this one tiny little edge case. But cargo SemVer checks is deployed so broadly that one tiny little edge case broke 3 separate projects within a month. So that's the risk that we're facing. That's why it's so important to get this right. So the thing that I would like to propose that we do as a Rust project is that we should explicitly consider SemVer as part of the stabilization process for new features. I'll tell you why in a second. This is, broadly speaking, from a very high level, the feature lifecycle. Somebody has a brilliant idea, they write up an RFC, and then eventually it gets an unstable implementation in the Rust compiler. And there's a whole bunch of iteration that happens here. And then eventually, the feature is deemed good enough, we begin the stabilization process. We begin writing a stabilization report. And then we write a bunch of documentation explaining how this feature works, get diagnostics in order and everything like that. And then we stabilize. At no point at the moment is there a SemVer step in all of this. And I would like to add one. I think that we should insert an analysis of SemVer hazards as part of writing the stabilization report. This is important because it means that the person who is the absolute expert in that feature is helping find the edge cases that are notable and that are important to catch. That gives us more confidence that we nailed every single one of them, and it massively diminishes the amount of risk that we're facing in getting something wrong. If they thought about a SemVer hazard, they probably got all the edge cases right. I'm not very likely to, because I just read the docs and do the best that I can. And as part of thinking about what are the SemVer hazards in the report, we write documentation. Well, we should update the documentation because we have a page that lists all of the known SemVer hazards. Cargo has a reference, and we should add documentation on whatever we found in the stabilization report into that reference. This is good not just because now we have more complete documentation, it's actually good because now cargo SemVer checks can cite that documentation in explaining why the lint is there, why the breakage that we detected is actually breaking. So instead of us improvising with the diagnostic messages that we show to users in the few lines on the CLI that we have available for showing what is broken, we can direct them to a very well thought out piece of documentation with examples and explanations that will explain away any questions that they might have. That'll be a wonderful user experience. And if we can slip in these 2 extra steps into the process, then I think it'll be very, very likely that by the time the feature is stabilized, we should be able to have cargo SemVer checks lints available for that feature on day 1. And I think that would be awesome, because it is a glorious experience for users to know that they're protected while using that new feature from day 1. All right, so that closes the chapter of why we might not have known what the right rule is. How about not having the right data? Consider this example. Here we have a crate, and it just re-exports the API of another crate. And now we're making a change. We're just bumping the major version of that dependency, so we're re-exporting completely different items and types from the perspective of the Rust compiler. Obviously, major breaking change, right? This is not something that we can catch today, because we build the rustdoc JSON of the crate that we're analyzing. That rustdoc JSON says nothing changed. There was a re-export before, and there is a re-export now. So from our perspective, there is nothing to SemVer check here. No items have been changed, and so we're just going to say, no changes, you're good. That's a false negative. That's unfortunate. The problem here is that there's no reliable way for us to glue different rustdoc JSON files together. The rustdoc JSON output that we get just has insufficient information. We don't know how to connect things because there might be multiple major versions of a given crate that are available at any one given time, and we just don't know which one of them should be using. And because we don't have the right information in the rustdoc JSON, we just conservatively say, nothing to see here, we can't check this case, this is just a false negative. This is not an easy problem to solve. The reason it's still here, why I'm talking about it after 3 years of building cargo SemVer checks, is that if it were easy, we would have solved it. So it's a very challenging problem. And it actually requires a pretty complicated dance between rustc, cargo, and rustdoc to get us all of the information that we need. It is necessarily a cross-team problem. It is not just rustdoc needs to do this one thing and then the problem is solved. And so you won't be at all surprised to hear that progress on this problem has been made one conference at a time. The last time that we met in person at Eurorust last year, we got in a room, we hashed out something that we thought would be decent, and moved on from there. I believe we're going to make more progress this time around, so I'm very happy that this is a longer conference as well. But that's actually not sufficient by itself. Solving cross-crate linking also causes more problems. Remember earlier how I said that building the rustdoc JSON for the crate that we're analyzing is 90 to 95% of the runtime? Well, if we build a lot more rustdoc JSONs, we're going to suffer really, really bad regressions in runtime. And if a tool is slow, then fewer people use it, which is just regrettable. So let's try to solve that problem as well. Let's try to avoid the performance cliff. One of the ways that we could do this is when we are linting this crate that re-exports something, we'll notice that the thing that is being re-exported, odds are, is actually in crates.io. It's a well-known version. And so if you ask, what are the items in this? What does the rustdoc JSON look like it? And when I ask for it, it's actually the same rustdoc JSON, so long as we're on the same platform, caveats apply. But more or less, they're the same items. We should be able to reuse the rustdoc JSON. Can we avoid rebuilding it? Can we just use a ready-made rustdoc JSON somehow? I hope so. Again, these are half-baked ideas. We're approaching it with the mindset of, let's see what would it take. And so one option is, docs.rs already builds rustdoc HTML. Can we get it to also build rustdoc JSON and just host it? And this is a half-baked idea for a variety of reasons, like the rustdoc JSON format keeps changing versions and so on and so on. But it's not a terrible idea, and I'm pretty sure that we can work out all of the edge cases if we decided to. Another option would be cargo publish is already verifying that your package builds, right? It's essentially doing a cargo check for you. Well, the cargo check portion is the expensive bit. The writing down the rustdoc JSON once you have everything you needed is not actually that expensive. Could we get cargo publish to build the rustdoc JSON and just upload it as part of crate metadata somewhere? Again, lots of things to work out. This is a half-baked idea. But I'm pretty sure that, again, if we sat down, we could probably figure out some way to get this to work. The point in showing you all of these examples is that I think that there is a solution in the solution space here, not to try to get us to get to any particular solution. I think it's a problem that's worth solving, and I think we can solve it. All right. So upstream broke SemVer was one option. How about when we have a breaking but non-major change? In this case, Alice and Bob agreed that Bob did the right thing, right? Bob released a minor version because the change was not decided to be major by the, for example, API evolution RFC. But that's not any consolation for Alice. She still ran cargo update, and she's still, holding the pieces of her broken project. So that's just unfortunate. An example of this is if we have, for example, a struct that wraps a string, and we have this asref implementation that lets us treat it like a string slice. So when we use it as a string slice, we do this asref call, and then we can do len on it as a normal string slice. Easy. Now we add another asref implementation to a byte slice, and all of a sudden, all hell breaks loose, because the compiler no longer knows what that asref call is talking about. And it will give us this helpful error message. It will say the type must be known at this point. Data.asref is the problem. And the suggestion says textblop as asref t is the thing that is confusing. So we need to make an explicit choice of which trait we're calling asref on. The specific problem here is that the compiler cannot figure out that t parameter in the middle. Everything else is fine. It's just that t that's the problem. But this also hints at the solution. The compiler was always doing this kind of rewriting under the hood. It always was figuring out what that t is. And in the previous version, this worked fine. So can we just figure out what t was in the previous version and go from there? Here's what I'm thinking. Imagine a future hypothetical cargo fix -- update tool. Or maybe it's a separate tool like cargo SemVer checks. And it does something like this. If you ran cargo update and now your project is broken, it does a couple of things in order. First, it records all of the broken call sites. We already have this diagnostic information from Rusty. It's data.asref in that file and that line number. And then it rewinds the update. It goes back to the previous version that was known to build and asks inference, hey, what's that t thing in there? Oh, it's string. Okay, great, like stir slice. Perfect. Let's fill that in. It reapplies the update and it fills in the inference result. It rewrites your code to use the explicit form with all of the type variables that were previously inferred. Okay, great. Let's see if that worked. We run cargo check. One of two things could happen. Either everything's fine, in which case, great, we solved the problem. Yay, no more breakage. Or we didn't solve the problem, but we're not really worse off than before. The project was broken to begin with, so we just undo all of the changes that we did, and we just throw up our hands and say, hey, user, sorry, you need to fix this. We can't do it for you. This is, again, not a full flow, and it will not solve every kind of inference breakage, but it will solve kind of a lot of them, I think. So the point of this is that we can 80-20 our way to problems being sort of arbitrarily small. I'm pretty confident that, just like with cargo SemVer checks, we can make inference breakage a lot less annoying by having tools like this. All right, so breaking but not major change out of the way. Is there a third option? As it turns out, there is, and it's perhaps the most unfortunate one of all. Alice and Bob disagree on what happened. There was a piece of the API that was maybe public. And that's really sad. Here's how that happens. Bob wrote this code. There's a public struct that has some fields and derives some traits, partial, ORed, serialized, deserialized, things like that. And in version 1.1, Bob shipped a tiny little change, just reordered the fields, but it's the same struct, right? It still has the same fields, it still derives the same traits. It's all good, right? Well, as it turns out, derive partial ORed derives the partial order in the order of the fields in the struct. And because we changed the order of the defined fields, we changed the sort order. Now, is that a problem? I don't know. Alice was using Bob's code. So she was generating some vector of data types, and she was sorting that vector and just persisting it to disk. And then later in the application, maybe loads it from disk and then does a binary search over it. It was sorted when we saved it to disk, so binary search should be fine. So one day, Alice goes through this flow, generates a bunch of data, sorts it, saves it to disk, and then runs cargo update. And after cargo update, she loads the data from disk, and all of a sudden, the binary search is broken. There's an item right there. She can see it in the serialized format on disk, and binary search says, sorry, that data is just not present. So this code is objectively broken, but whose fault is it? What happened? The problem is that the sort is wrong. It's sorted, but with the old ordering. It's not sorted according to the new definition. And so the thing that happened is maybe major change. Alice will go open a GitHub issue on Bob's repo and will say, hey, you broke the public API in v1.1. And Bob is like, I don't know what you're talking about. And Alice says, the sort order changed. And Bob says, sorry, that was never public API. We implemented partial ORed. We still implement partial ORed. We always promised there would be the ability to compare things, but we never promised a stable order. And now Alice is upset with Bob. Not only from her perspective is her project broken, Bob is refusing to take accountability for what happened. And that is a very, very reasonable thing to think. From Bob's perspective, he's an open source maintainer. He's not paid to do this. Alice was just using some crate that she found in crates.io. And so his burnout intensifies. He probably thinks about going to retire to a mountaintop somewhere. So the question I want to ask you is, who was right? Because I sure don't know. This is the difficulty of this problem. This is a socio-technical problem, and the socio part is at least as hard as the technical part. And the best way to solve this is to just be more explicit up front. Now, we actually have concrete examples of Rust allowing us to opt out of API guarantees explicitly. Non-exhaustive is one of them, and I really love it. Target feature, which we talked about earlier, is also another one. Instead of a function being callable at any time, target feature might say, actually, you might not be allowed to call this function in certain contexts. So there is precedent for this kind of thing, and we just need to lean into it and add more of these kinds of features. What we want is explicit guarantees that are machine checkable. Here's an example of what that might look like in the concrete use case that we were just talking about. We might add an attribute that obviously needs a lot of workshopping, but this is what I'm calling it right now. SemVer exclude stable order. Now we can determine which code was wrong. If you explicitly said, this is partial ORed, but it does not have a guaranteed stable order over time, then you cannot sort and then save to disk and then update and then reload from disk, right? Whenever you get a piece of data from disk, you cannot assume that it was sorted. You have to sort ahead of time. And if you didn't have this, then obviously that assumption was maybe fine, or we could decide this in collaboration with the Lang team. They're specialists at this, and I'm not. And importantly, just like adding target feature and non-exhaustive, adding this after the fact to an existing type is a major breaking change, and that is something that we can lint with cargo SemVer checks. So not only are these more explicit guarantees helping users avoid these contentious situations where they're both pointing at each other and at deciding who is wrong, they're actually helping cargo SemVer checks prevent this kind of issue from happening in the first place. All right, so these are the 3 possible cases that we might be in. Upstream broke SemVer, there was a breaking but not major change, and the change was maybe major, and Hiram's law made somebody rely on something that they maybe shouldn't have. What I'm asking all of us to do is to have empathy for imperfection. None of us here is perfect. The SemVer study showed that. We all ship SemVer violations, and I will definitely throw myself under that bus because I've definitely done it. And the important thing to note here is that our users are imperfect as well. They make mistakes. They're impatient. They don't read the docs. They make bad assumptions. They rely on things that should not be relied upon. And the more we make Rust an accessible language to everyone, the more users we'll have and the more imperfection there will be. So this problem is not going to get better over time. It's going to get worse. So I'm asking us to remember that Rust leads by example with empathy. I think Rust is the most empathetic language, most empathetic programming language out there, but I don't think we should stop at that. I think we should keep making it even more empathetic over time. So hopefully by now I've convinced you that eradicating unintended breakage is not easy. It's actually a very, very, very hard problem. So this is not going to be a quick fix. But I think it's a problem that's worth solving. We need to have a user-centric view that's not centered on any component. This is not a compiler problem. This is not a lang problem. This is a problem that affects our users and needs everyone's participation to be solved. We need a how can we do it attitude as opposed to it can't be done attitude in order to solve it. Because a lot of these problems are solvable, but we have to decide that we need to solve them. We need to carve out space and time for cross-team work, which is why I'm very grateful that we're having an all-hands attached to this conference. It's going to be super helpful. And we need to lean into idea sharing, having determination, and hopefully finding years worth of funding, because this problem is not going away this year or next year. This is maybe a Rust 2035 kind of thing if we actually want to eradicate it. But I do think it is a problem worth solving. I think we want to eradicate accidental breakage. And now that we know the way, I think we should say, let's get going.
Thank you very much. I think we have time for a couple of questions, if anybody has them. Ah. Looking too high, sorry.
So you suggested that we'd have some way to specify that something doesn't have a specific guarantee, but there's also the opposite direction of by default not having guarantees
Right.
and saying you specify more of them. Do you have opinions on that direction?
Not particularly. I have an opinion on having a default understanding of what is the, if nothing is specified, what is specified. I think this is more of a lang team question. Cargo SemVer checks will just do whatever is right. A lot of the time we see these norms sort of come up in the ecosystem and then get sort of, happen the way that they came up. If we manage to get ahead of it and make a concrete choice, awesome.
Right. Nico.
Great talk. I'm
Thank
all
you.
in on the big picture. I'm curious about something, which is you described sort of cargo fix -- update. I was wondering about cargo update without a -- fix. And also, in other words, part of updating your dependencies is fixing your code. I'm also curious about the idea of letting crate authors kind of annotate and specify how those updates should be done, right? Give hints to the compiler. Have you thought about that at all?
Absolutely. In fact, an earlier version of this of that slide said cargo update -- fix because I did not dare presume that we would want to, include my suggestion into mainline cargo update. If that's an option that we're willing to pursue, I think it would be a fantastic idea. I also think that because cargo SemVer checks can generate lint reports on what changed, we might even be able to extend that and say, hey, actually, here's a code mod that is required by this change, right? So that we can make cargo update work across breaking changes as well, right? So we know what broke. This function takes an extra argument. Okay, it is required to have a code mod that fixes that. The default value of that argument is 0. Great. Rewrite the call site accordingly. That is also something that we can lint. of course, the limiting factor here is time and funding. So all of these ideas are great, and I think they're absolutely doable. We should do them. The question is finding the time, space, and money.
I'm sorry to say that we are at time, so I know there's a few more questions. I'm sure that Predrag would be more than happy to talk with everyone about this. Thank you again to Predrag.